All right. Well, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class. Help us use this time wisely to understand a little bit more about calculus, Lord. In your name I pray, Lord Jesus. Amen. So, yeah, I just wanted to cover some sort of random tidbits that maybe we didn't really see in the regular course as emphasized. Now, this was emphasized, but I thought this is a good place to start because have you guys factored them yet? Factored one of them. So this one? So you got what? X plus 5 squared. And then we have minus 25 minus 1, which is minus 26, right? So that factors to x plus 5 plus the square root of 26. X plus 5 minus the square root of 26. So this is completing the square, right? Is that what you got?
I got plus 24 minus 24. I think I accidentally used subtract. I accidentally used
Oh, maybe. So you'd be right if it was a plus 1 instead of a minus 1 there. Yeah. But unfortunately, it's minus. So this is completing the square, right? It is the fastest way to factor. It is by far, the most reliable. Like, I can complete the square on any quadratic, and I can be assured that I have factored it, So it's important for everybody to learn this and to know it. Now this 2, what I do here is I factor the 2 out. Right? I factor 2 out, then I've got x squared plus 3 halves x. Oh man, that was dumb. I'm sorry guys, I did not mean, you guys should have been able to factor this one.
I did.
What did you do?
I just had 5 times x squared.
That's right, because with the x squared there, it's not factorable, right? I meant to put an x there though, so sorry about that. Yeah, that was irreducible with the both of them being squared. Like, you couldn't reduce it, So this one here, 3 halves, and then plus what? Plus 10? X plus 10. So that's what I do. I factor a number out to make it the leading coefficient 1, right? And then I take 1/2 of whatever's here. So I take x plus 3/4, square that, right? And then I do what? I subtract 3/4 squared, which is 9/16, and I add 10. But let me write that 10 suggestively as 160 over 16, right? And so what you got? You got 2 times x plus 3/4 squared minus, plus actually, plus, right? Plus 151 over 16. What does that show us? That shows us that this quadratic, it can't be factored over the reals, right? It's what's called an irreducible quadratic or a prime quadratic. What does that mean about the graph? That's right, never crosses the x-axis is what that means. Now, of course, if I, instead of factoring over the r, if I just cross that out and put complex numbers here instead, then all of a sudden we can make progress, right? We can go, well, that's 2 times x plus 3/4 plus, I square root of 151 over 4 times x plus 3/4 minus I times the square root of 151 over 4, right? So it does of course it factors over the complexes, as does everything, right? Do you guys have any questions about factoring or anything? So you guys are good to go? Okay. I think both of you are actually really strong on factoring. I just wanted to take a second to remind you guys, like, completing the square is something we need to know. So let us turn the page here and think about something completely different. So if you're given a function, what when can you know, what can we say about a function from the reals to the reals? Or let's be a little bit more general. So we got a function from one set to another. And there are two basic properties of the function we can talk about, which is one-to-one and onto, right? So what does it mean for a function? Well, first of all, what's a function? Do you guys know? Like definition.
The definition of a function
Yeah, if I've got like,
is a permutation of an x such that it matches a single y. Multiple x's can match one y, but not multiple y's matching an x.
yeah, right. So it's a single valued assignment of each element in A to some output in B, right? And like you said, the outputs could match up, but for one input, there's only one output, right? So a single valued assignment is one way you could say it. Now there are a more sophisticated way to make that precise in terms of set theory, but we'll just say single valued assignment, because that's kind of the heart of the matter, right? So, and so we could also write it like this: x maps to f of x. That's an element of B for each x in A, right? So there's more notation we can talk about here. We say A is equal to the domain of F, right? And we say B is equal to the codomain of F, all right? What else can we say? Well, there's other things that we can talk about for a function that maybe we haven't talked about before. If we have U is a subset of A, we know what that means? What does it mean for something to be a subset?
It means it's a set that all the elements of the set are within the set
Mm-hmm.
of A.
Right. So a way to make that precise is to say U is a subset of A if and only if X, an element of U, implies X is also an element of A, right? They could say that. Anyway, so if we have a subset of A, then we can talk about F of U. This is equal to, what's this mean? Well, this means F of X such that X is an element of U. So this right here is the so-called image of U under F. All right? When F of U, excuse me, not F of U, listen to me. When F of A, when the image of A under F, when F of A is equal to B, well, let me just say this. We say F of A is equal to what? This is equal to the range of F, right? The range of F is the set of outputs, right? Set of outputs. And when F of A is equal to B, then F is onto, or surjective, you could say. So a surjective map or a onto map or a surjection, these are all synonymous. That means that the range is the codomain. In other words, everything in the potential outputs is actually attained, right? This is an onto map. There's also something else. If V is a subset of B, then we can talk about the inverse image of V. What's that equal to? So what this means, so what we're saying is X, an element of A, such that what? What should this? How should this be defined? What does this mean? This is called the inverse image of V under F.
X is equal, f of x is equal to v.
F of x is not, well, equals to V wouldn't make sense, see, because f of x is an element, V is a set. So we can't have set equals element, but we can,
An element.
an element of V, that's correct, that's the definition. So what the inverse image of V is the set of all things in the domain which map to V. The set of all things in the domain which map into the set V. Notice that this does not mean, caution, like let me make a cautionary remark here. Fundamental confusion students get into here, which is that, let me just say this remark, F inverse as a function need not exist. In this context, I didn't tell you enough information about the function to be sure that the inverse actually exists. So it doesn't have to. All right. So there's, we got domain, we got codomain, we've got range, right? We've got forward image, we've got inverse image. There's one other fundamental definition that we talk about for functions. All right, and this is across all courses, right? This is not special to Calculus 1. This is just math. This is really set theory, right? Which is if let's say if for x1, x2, an element of A, I'm saying this wrong. I'm sorry. It's not coming out right. Give me a second here.
By the way, can you explain codomain again?
Codomain is the set of potential outputs, whereas the range is the set of actual outputs. That's the distinction. So you can always make, for like a real valued function, we can always just make the codomain the real numbers. That doesn't mean all real numbers are actually reached. So it's kind of like, it's the playground where you're playing, but you don't have to get to every toy or whatever, or something like that. Whereas the domain, you have to give a prescription on how to map every single thing in the domain for a function. There's an asymmetry in the role of domain and codomain. Okay, so let's say it this way. Let x1 and x2 be elements of A. Then if f of x1 equals to f of x2, all right, implies x1 equals to x2, then f is a 1-to-1 or injective function. So this is another special property a function can have. It can be injective. It can be 1-to-1. All right? An interesting thing to think about for a 1-to-1 function is like, okay, so in calculus, let me just take a step back for just like functions from R to R. Let's talk about functions. Let's drop back from this abstraction for a second here. Let's just talk about example 1. You have a function, it's a mapping, say, from R to R, right? Then, so here's some potential graphs, right? There's a potential graph, right? Here's another potential graph. Here's a third potential graph. All right. So in each case, I'm giving you a curve, which might be the graph of a function. So my question is it the graph of a function, right? And if so, is that function one-to-one? So what's the answer for the first one? So what's the graph, by the way, definition, right? The graph of f has to be equal to x comma y, such that y equals to f of x, and x is an element of the domain of f. Quiet. Oh. Huh. Interesting. Student I haven't seen for a little bit. He's gone to grad school and stuff, coming back to visit. Okay, so so you guys tell me, the first one, function or not function? Why not? Daniel says not a function. Why?
Because it seems at the y-axis, the x is split into two different points.
Right. So if we draw this vertical line, we can look at these 2 points here, and what do those mean? Those mean that f of that x, let's call, that of x is equal to y1 and y2, right? That is not single valued. Therefore, this is not a function. So if the graph fails the vertical line test, it's not a function. Yeah?
What's interesting is that is also not a function of y.
That is also true. It is also not a function of y because it fails the the horizontal line test as well. Yeah, good point. How about this one? This is a graph of a function, and you're fair enough. So let's talk about, I'm talking about functions of x. Yeah. So we'll talk about functions of y here before long. But so here, is this a function? It's a function. Is it a one-to-one function? No. See, because if we look at the horizontal line test, we can see there's 2 points of intersection. The reason the horizontal line test is interesting, just think through it. So here's your x1, here's your x2, right? And we have f of x1 equals to f of x2, right? Yet x1 is not equal to x2. So that is logically opposite to the definition of one-to-one. So this is not a one-to-one function. But then finally, the third graph, potential graph, right? This right here, this one, y equals f of x, is in fact, one-to-one function, right? Now,
Depends on if all we can see is.
oh yeah, fair enough. So let me take the ambiguity out of it. There you go. But fair enough. Like I was always bothered by this as a student because they asked me a question about a graph with arrows on it, and I'm like, what happens past the graph? I can't answer your question. But like, you can't be that way. No one's that careful, except mathematicians. So yeah, interesting. But yeah. Okay, so question. For a one-to-one function, what can we say about the inverse? So a singleton is something. What's a singleton? Singleton is a set containing one element. In contrast, this thing, which is this thing, is the empty set, right? So that's a set containing no elements. A singleton is a set containing just one element. Let's think about this. If we have a one-to-one function, what are the singletons? What's the inverse image of a singleton of a one-to-one function? So that's my example 2 here, which is kind of a question. For F injective, right? Describe the inverse image of a singleton. So let's write it down logically, right? What is the inverse image of the singleton? What does that mean? What's that notation mean? And so here sometimes people abuse notation and they'll write F inverse of P. Like it's a common shorthand to write F inverse of P to mean F inverse of the set containing P. That's a common abuse of notation. All right, just saying. But what does this mean? This means X and A, right? Such that what? Such that F of X is an element of the set just containing P, right? But we can be less dumb, right? We can be not so dumb. We can just say, okay, so X is an element of A such that F of X equals to what? P, right? So what do you guys think? Is that, for an injective function, what can you tell me about this set? Like let's suppose we had x1 and x2 in this inverse image of a singleton, right? What would that mean? Not x1 equals to x2. I mean f of x1 is equal to f of x2, right? Because they're both equal to p, right? But f is what? F is injective, right? Therefore, what can we say about x1 and x2?
X1 and x2 are equal.
They're equal. That's right. So that implies that x1 equals to x2 since f1 to 1. So can you describe the inverse image of a singleton? What is it? So therefore, the inverse image of a singleton is a singleton, right? Do you believe me?
Yes.
Or have I trapped you? Because in fact, this is only sometimes true. Even for a one-to-one function. For example, let us suppose we define f of f from, say, 0, 1 to the reals by f of x equals to x, right? It's a pretty simple function, right? So here's the graph. Right? So we start at 0, 0, we end at 1, 1. You can think of the inverse image of a point in terms of the intersection of a graph with a horizontal line. See, because, like here, if I look at this line, right, suppose that this intersection point here is at like 1.5, right? So what's f inverse of 1.5? If you want, I can make this more snazzy. Let me make that an x squared. There. Now I've made it all fancy. That doesn't change the endpoints, but it does make it slightly more exciting. Yay! all right? So what's the inverse image of 1.5? In other words, which x in the domain maps to 1.5? Now you might want to tell me the square root of 1.5 maps to 1.5, but you're not allowed to do that because that's not in the domain, right? I made the domain 0 to 1. So you can't get to what you need to get to do that. So this is actually the empty set. See, only down here, for instance, if I look at, like A for 0 less than or equal to A less than or equal to 1, and then I say, well, what's the inverse image of A? Well, that is x in 0 to 1 such that what? F of A, right? Rather f of x. So x squared equals to A, right? Right? So then what? That's just what? So and that is just, it's a singleton. It's just the square root of A, right? So that, of course, right here, square root of A is the point which maps to A. So there's this interplay between horizontal and vertical lines and the inverse image. You can think about these things. So the answer to the question in example 2 actually was that the inverse image of a singleton is either, for an injective map, all right, for a one-to-one map, the inverse image of a singleton is either a single point, a singleton itself, or it's just nothing. When it's nothing is when the singleton is outside the range. See, the range here was 0 to 1. 1.5 is outside the range. That's why the inverse image was empty, right? You guys good? All right, so so definition, if f mapping from A to B is 1 to 1 and onto, then f inverse from B to A is defined as follows. Here it is, f inverse of y is equal to x if and only if f of x is equal to y. And that's for each, y in B and x in A, something like that. Why can we define the inverse like that?
Because if it's 1 to 1, then say the graph of f inverse of x would be f of x but rotated 90 degrees.
Oh, this is true. Yeah.
But if it were not 1 to 1, then f inverse of x would not be a real function because it would not pass the vertical line test.
In the horizontal sense, right? Yeah. I agree, we could think about it that way. Think about it in terms of one-to-oneness, right? So you tell me, I have f inverse of y equals to x1. I have f inverse of y equals to x2, right? Why is it that those two values have to be the same, right? Because that's what we need for f inverse to be single valued. Why is it that x1 and x2 are equal?
Since it is 1 to 1,
Mhm.
you can take the standard function in both sides such that it's y is equal to f of x.
No. You're not thinking about the definition. I mean, you're right. But this is the definition, right? We have to work with the definition. So here, you have f of x equals a y, right? So we've said, what does it mean for f inverse of y to be equal to x1? That means that f of x1 equals to what? Right, and this means,
F of x2 equals to y.
right? So f is 1 to 1, therefore f of x1 equals to f of x2 implies x1 equals x2, which is what we need to say it's single valued. Now, the other thing we need is that the domain of the inverse function is all of b. How do I know that that's reasonable? How do I know that there exists an x such that f of x equals to y for every y in b? Well, that is given to me by the assumption of onto. See that the fact that the function's onto means that it hits everything in b, which means that I can find an x that maps to y, right? Now, what you were saying about graphs is wonderful. That's true. Like that's a legitimate way to think about it. I'm just encouraging you to suppose you don't have graphs. Suppose all you have to work with is sets and logic. Like, how do you think about inverse functions? This is what I'm trying to talk about for a second. All right. So, in short, injectivity is what we need in order to define an inverse, right? Like, let's take a step back and let's try to be a little bit more creative. So here's a question that I try to talk about with math majors at some point. Oops, I forgot to. Oops. Well, anyway, you guys are here. How about this? Suppose I give you a function, right? And then I say, well, make it invertible. How could you do that? Is it possible? Like, let's look at some specific examples and see how that works, all right? So like, okay, so let's start out with example 3. Can you tell me how to make example 3 invertible? Why is it not currently an invertible function? According to my silly definition of invertible, yeah. By the way, I think other people might have slightly different definitions of invertible, so you're gonna have to kind of like look at the book that you're looking at, exactly how they parse the terminology. Like, some people do different things with codomain, is what I'm trying to tell you. Yeah.
Currently, it's not onto.
Currently, it's not onto. How can you make that function onto?
You can add a piecewise defined section separately.
Oh, you're saying extend the function. Interesting suggestion. So that's one thing you could do. So you're
So maybe like it's
we can just do it. We can just do it with a picture. I'll just
x squared above 0 and negative x squared below 0.
Oh, okay, cool. So you're like, just extend it like this here, and then like there. So you're basically saying your new function, let me call it f tilde of x is equal to, like case-wise defined, basically x squared for x greater than or equal to 0, and minus x squared for x less than or equal to 0. Then that function, of course, but once you do that, you did what? Now you're like f tilde is a mapping from R to R, right? So you chose to expand the domain and extend the values in such a way that it's both onto and one-to-one for the reals to the reals. Neat. I like it. If you do that, what's the inverse function?
The inverse function is, well, like above 0 is x, it's square root of x, and below 0 is negative square root of x.
Let's see here. So you're telling me I like to use y for the inverse function. All right, so like f tilde inverse of y
They're actually,
is equal to, so you got like square root of y and minus the square root of y down here.
so from 0 to infinity, it's minus the square root of y. 0 to infinity, it's, yeah, I think it's minus the square root of y. And then from negative infinity to 0.
No, I think you're right. I think it's square root of y. If you take this graph and reflect it across the line y equals x, you get square root. It's fine. It's fine. Like, so really to find the formula for the inverse, you're solving, y equals to x squared for x greater than or equal to 0. That tells us that, x is equal to the square root of y. We have to put plus square root there because x is greater than or equal to 0. So it forces us to choose that radical in the solution. On the other hand, for the other case, you've got y equals to minus x squared for x less than or equal to 0. That implies that x is equal to minus the square root of minus y, actually. So this formula is not right because it doesn't make sense, because we'd have an imaginary number there, so we got to put 2 minuses, yeah? And if you think about this graphically, it makes sense too, see, because, yeah?
You could also just, instead of putting 2 minuses, you could put an I outside.
Oh, no, we can't do that. No, because then we'd have imaginary. This is not an imaginary number.
Yes, but if you multiply imaginary times imaginary, that equals
Oh, you're just saying write it as, oh, that's an interesting idea. So you're saying minus I squared of y? I don't think you're wrong, but that's
or maybe just no one. I'm not sure.
that's a funny way to think about it.
Because if you take the square root of -1 times the square root of x squared, that's fine.
It would be like minus I.
I mean, what I'm trying to say is you could say that the square root of minus y is equal to the square root of -1 times the square root of y, and that would be okay, I think, here. But you got to be careful with these kinds of things, because complex arithmetic is more subtle than it seems, although the square root is pretty forgiving. But that is a completely real formula. That's the inverse, and it does exist. So you did it. That's good. That was not what I wanted, though. So I wanted you to be lazier. So example 4. All right, so you're given, I'll have to recreate the magic, f of x is equal to x squared for, x an element of 0 to 1, right? And we were saddled with the mapping going from 0, 1 to the reals, right? So what's another thing we could do? Okay, so let me ask the question a slightly different way. Suppose I ask you to make an invertible function and I deny you the freedom of extending the domain. What do you do?
Set y larger.
Set y larger than 1? So again, the question is modify function to make, let's say, f tilde invertible. Let me call it f. Instead of f tilde, let's call it f bar invertible. But f bar has to be a mapping from 0 to 1. And also, I insist on having the same formula, to be clear. How do I make it onto? Because that's all that's missing, right? The function is 1 to 1 on its domain, right? It is 1 to 1 on its domain, so how do I make it onto? It's so stupid. It's just stupid. You make the codomain 0 to 1. See, because those are the y outputs. This function outputs 0 to 1, right? So if you just make its potential outputs its actual outputs, that makes it onto. We always have this freedom to take the codomain and just get rid of everything we're not mapping to. It's a stupid thing to make any function surjective. We can make any function surjective simply by doing surgery on the codomain. Just cut out everything you're not mapping to and you got a surjection.
So it's not mapping to R anymore, it's just mapping to 0, 1.
That's right. Now it's 1 to 1 and onto. And so f bar of x is just equal to x squared, right? And so if I set that equals to y and I solve for x, which of course is, to be clear, x is 0 less than or equal to x less than or equal to 1. That's the context of this algebra. Well, you solve for x, what do you get? You get x equals to square root of y. So therefore, f bar inverse of y is just equal to the square root of y. So these things we're doing, and I'm very happy about your idea to extend the domain. That's very cool. So let me just show you some notation. Actually, I don't have a notation. I actually don't have a notation for this surgery on the codomain thing. I don't know of a standard set theoretic notation for that. But this thing you did with changing the domain, there is notation for that. And the notation is like this. So what you would say is that your f tilde restricted, this is the restriction bar, restricted to 0, 1 is equal to f. Although, oh man, see there's some fussy things about, maybe there's some fussy things to say about codomain here, but I'm a little worried. I need to put some scare quotes in here. This is why I need to teach Math 200. There's a couple of kind of fussy things here I need to think about more, but I would say that is the restriction of your extension is the function we started with. So something we can do is we can restrict a function or we can extend a function to try to give it properties that we like. Right? What if your function is hopelessly not, like what if it's really far from being 1 to 1? You could have something like this, f of x equals to x squared is the standard example I give. The trouble with this, right, is that when you look at the inverse image of something in the range, right, what happens if this is like, I don't know, b, let's say. I guess we could call it y naught. I mean, why not? Sorry, that's horrible. F inverse of y naught, well, it's two things. See, it's minus the square root of y naught, and it's the square root of y naught. See, it's got two things in it, usually. So one way of thinking about injectivity is if the inverse image of a point is not a singleton, that means it's not a 1-to-1 map. You need the inverse image of every point in your inverse image of every point needs to be just one point in your domain to get an injection. So, yeah. So anyway, I just wanted to start talking about these ideas with you guys. I go into these ideas more deeply in like Math 200 and like later math classes, but I think it's important for us to start talking about them here. So now we've done it, all right? Now, the harder thing I wanted to talk to you guys about today was something that's like a lot deeper, which is the, well, let's see here. Let's just start with a kind of as a segue between this part of the talk and the end of the talk, which is a proof. How would you define these following things using limits? So, first of all, how would you define a function having a vertical asymptote in terms of a limit? Well, if I have a vertical asymptote at x equals to a, what does that tell you about how could you express that in terms of a limiting process? So let's see here. X equals to a is a vertical asymptote. If you don't mind, I'm going to abbreviate it. It's vertical asymptote VA, yeah. How would you express that in terms of a limit? What else? I have four other questions for you guys to think about. How about you've got a hole in the graph. At x equals to a. How would you explain that in terms of a limit? What if you've got a finite jump discontinuity at x equals to a? How would you define that in terms of limits? For you've got a horizontal asymptote. Let's say for x much, much greater than 1. How would you define that in terms of a limit? And then finally, last but not least, how would you define continuous at x equals to a in terms of a limit? So you guys, any ideas? The first one?
Limit as x goes to a.
Equals to what?
Depending on the function, either positive or negative.
Right, like plus or minus infinity, and so like there's a lot of special cases to think about here, right? We could have like from the left the limit's infinity, from the right the limit's minus infinity, but basically whenever either one or both of the left or right limits as x goes to a is infinite, it's a vertical asymptote. So a vertical asymptote at a point implies the existence of an infinite limit, either from the left or the right or both. Hole in the graph, what would that mean? That would mean that the limit as x goes to a of f of x is equal to L, but f of a does not exist. So the limit exists, it's something finite, and yet the value of the function's not there. If you think about it, that's what a hole in the graph is about, right? Something like this. You've got a hole, right? So that hole is maybe at a comma L. So if you think about that, right? That means that the limit exists, it's equal to L, and yet by assumption, f of a does not exist. That's a hole in the graph. Do you guys know how to put a hole in the graph anywhere you want? Like, suppose I want to put a hole in y equals f of x right here, let's say at minus 1. What I can do is I can do y equals g of x, and my g of x will get this, watch this. That is a mathematical hole puncher. See, because that's not defined at minus 1, and yet it's equal to 1 everywhere else. So that just punches a hole in the graph at minus 1. In some sense, that's what all holes in the graph are. They're just that, somehow hidden in the formula, in the formulation of the function. How about finite just jump discontinuity? So what's that look like? We've got like this on one side, right? We got like this on another. The value of the function may or may not exist at A. It doesn't really matter. The point is that this is L2, this is L1. They're not equal. And we have, limit as x goes to A from the left of f of x is equal to L1, which is not equal to L2, which is equal to the limit as x goes to A from the right of f of x, right? That's a finite jump discontinuity in terms of limit. How about horizontal asymptote? That is just the limit.
X goes to equal to whatever the asymptote is.
Yeah, let's say L. That would make y equals to L the horizontal asymptote, absolutely. Continuous at x equal to A, what's that mean? That means the limit as x goes to A of f of x is equal to f of A, right? That's continuity. Now, some fine print here. That assumes that A is a point in the interior of the domain, right? We modify this definition to be a left or a right limit if A happens to be an endpoint in the domain, right? And we can make that more precise using epsilons and deltas, right? So I don't have enough time today to do everything I wanted to tell you guys about epsilons and deltas. But since I'm not sure we'll have a chance to meet again, I wanted to make sure I do a proof of something. There's really two major things I wanted to prove for you guys today, and a third I just wanted to show you. So let me get out the well, goodness. Trying to decide whether or not we should meet again. Maybe we should. What's that? Well, possibly. I'll tell you what, you guys don't mind, I'm going to use the projector and we'll talk about things together that way. We'll get a little bit more done that way. One thing I want to talk about for the remainder of our meeting today has to do with, there's a couple different things. I have a few results in the notes about sorry, I'm gonna close a couple things here. Go on, go away. Skedaddle. All right, here's one. So I proved in class a fair number of the limit law properties, but here's one I didn't show you guys in class because it was like a little bit too fussy. This is actually in my appendix, Jacob. I don't know if you did you see? I don't know if you saw this one or not. But like, how do you prove the product of the limits is the limit of the product? The limit of a product is the product of the limits. Is what I'm saying. So like, suppose you know limit of f of x is existing and limit of g of x is both existing, right? Like, how do you prove that? How do you select a delta such that the product of f of x, g of x, and these guys is less than epsilon? All right. So the proof here is a little bit sneaky. It involves like adding 0 in a kind of somewhat sophisticated way. So what I do is I add and subtract this term. All right. So I'm adding 0. And then if I factor out g of x here, and I factor out L sub f there, then I can use the triangle inequality to get this estimate, right? But the thing is, I control this, And I control that because I know that the limits of f and g exist, right? So I'm able to pick a delta that makes both this and that suitably small. So the estimates that I choose, they're a little bit sneaky. I choose a delta for f that makes it less than that. I choose a delta 2 for g that it makes it less than that. And I pick a delta 3, which makes the g of x minus that less than 1 as well. So with those three estimates in play, I make delta the minimum of all three of those things. So what that means then is that you get all three of these deltas at once working for you, you know? And then when I put that all together, I go back to the estimate that we looked at before. I have this is less than that. This is bounded by this. That's just L sub f. And then, of course, the algebra cancels out. You get epsilon over 2. This also gives you an epsilon over 2. Well, this doesn't give you epsilon over 2, but see there's like a 1 plus L sub f. So if I drop the 1, that makes the denominator smaller, which makes the fraction bigger, which this is obviously like less than epsilon over 2. So I've got straight up equals to epsilon over 2, something less than epsilon over 2, so that gives me epsilon. So consequently, I've shown that like the product of the limits is the limit of the products. I didn't do this one in class because it was like more, it was like, you know, a little bit harder than the ones I tested on you. But if you're a math major, it would be good to like just read through this and try to understand it. Maybe not before you're done with the course, but at some point, you know.
Would you like to be on the final?
It could be on the final. Would you like that?
I mean, you already made it, it's not late.
I can remake a final for you guys.
It's gonna take again.
You have to take it too. Let's see here.
Maybe you could make a new final for him.
Make a new final for him? All right, I see. All right, so I want to talk to you guys about the intermediate value theorem. But first I need to talk to you guys about the real numbers. So what are the real numbers? Do you guys know?
All numbers that are not complex.
All numbers that are not complex? No, I don't think that's going to work because you also have like other number systems that are not real, but are not complex either. Like say Z mod 2 or Z mod 12, like clock numbers. Anything, okay, so let me give you a actual answer. So this is a definition. So the start of my notes have a bunch of, by the way, these are my 2013 notes, which I'll try to send to your mom so you can look at with respect to the questions I'm asking and talking about today. But I'll eventually get to it. So I start with like a small discussion of set theory, but then I have a definition of the real numbers. So here is a definition of the real numbers. And in short, real number is a set which allows addition, multiplication, and it's a totally ordered field. What that means is that if you have a less than or equal to b and b less than or equal to a, that forces a equals to b. If you have a less than or equal to b, b less than or equal to c, that forces a less than or equal to c, the transitivity of inequality, and totality, namely that either a is less than or equal to b or b is less than or equal to a, right? Or is the mathematical or, so it could be both. But if it is both, it forces a to be equal to b according to the other axiom, right? This is what complex numbers don't have. Complex numbers have all the arithmetic, but they don't have the ordering. So complex numbers are a blessing in the sense that any polynomial can be completely factored over the complex numbers, right? But they don't have the estimates, the inequalities that we do in the reals, at least directly. You have to work with like the length of a complex number. That takes the role. Anyway, every number has a multiplicative inverse except for 0. And you've got these additive and distributive properties. That makes it what's called a field. Now here is what makes the real numbers real. See, because up till now, all of these things, everything up to this point, are also true for just the rational numbers taken as their own set. What's the multiplicative inverse of p over q?
Q over P.
Q over p, that's right. And that works for any non-zero rational number. Every non-zero rational number has a